Chapter 17, a natural progression from electric force, electric field to electric energy now. So we introduce the electric force, charges and electric force, but naturally then we talk about the energy due to this electric force and the electric field. So like we have the, potential energy due to the gravitational force, electric force is also similar. It's a conservative force. Electric force, like the gravitational force, is a conservative force. So it obeys the law of conservation of energy. So we need to introduce the energy associated with electric force. So the electric potential energy, we just drop that potential, so it is understood. So electric energy and potential. This word potential is not quite the same as potential energy. So when you say electric energy, we are talking about electric potential energy. Then on top of that, we also have something called electric potential. It's not the same as electric potential energy. So there's a bit of a confusion here, but we will hopefully clarify it. Okay, so the chapter title, if you want it to put it very clearly, should be electric potential energy and electric potential. Two different things. Okay, like electric force and electric field are two different things. So electric potential energy and electric potential is full stop. That is different from electric potential energy. We need electric potential energy defined previously, then we can define the electric potential in terms of electric potential energy. Right, the contents of this chapter, the subtopics. One, electric energy. We will introduce the electric energy properly. Then after defining the electric energy or the electric potential energy, then we will define the electric potential. Stop there. Okay. So it's not the same as electric energy. I know I'm repeating again and again, but I want to drive this through. Okay, so you don't get confused. Two different things. Number three, conservation of this electric energy. So like you know that gravitational potential energy, we introduce that, then we have this conservation of energy, which is the change in the kinetic energy plus the change in the potential energy is zero if the system is isolated. So now we can bring in the additional potential energy that comes from the electrical energy. So we'll incorporate that into the conservation of energy as a general. The number four, we'll bring these capacitors. We learned that in the previous chapter, model system. In biology, we have the two plates, which is our cells are kind of two plates, the outer membrane, the inner membrane separated, the charges are separated. It's like a capacitor, so we bring it in again. Number five, it is dimmed, so it is not covered in the lectures. Right, so the importance of learning about electrical energy is very apparent when we talk about the electrical signals in nerves. Electrical signals are the basis of information transfer in the nervous system. It is essential to understand how this signal arises. A fundamental problem for neurons is that their axons, which can be quite long, we talked about it before also, but we are repeating the problem, which can be quite long, right? The neuron, the axon of the neuron, they can be quite long. Spinal motor neuron can extend for 1 meter or more. are not good electrical conductors. They are not good electrical conductors. So, you need a very good conductors if you want to send a signal across. Otherwise, if it's not a good conductor, the signal will be lost. Although it will be diminished, right, because of the resistance in the conductor, if it is not a good conductor. Although neurons and wires are both capable of passively conducting electricity, they can still conduct. The electrical properties of neurons compare very poorly to even that of an ordinary wire. It's a very poor conductor. So to compensate for this deficiency, neurons have evolved a booster system. You must have learned this, the action potential and stuff, right? So what happened with the neurons, the way the signal is transmitted is entirely different from the way that signal is transmitted across a copper wire. Copper wire, the electron just flows, right? But that's not how it is happening with the electrical signal in the nerves. The electrical signal produced by these booster systems are called action potential, which here also referred to as spikes or impulses. The passage of the electric pulse through a nerve membrane results in a sequential change in the electric potential difference across all parts of the membrane. So why we are bringing it again? Because the concept of the potential, which we don't know yet, right, that has to be introduced. So the significance of that you have in your physiology also, the human physiology, how the electric signal is transmitted is the potential difference between the inner cell and the outer cell of the nerve membrane. This is the one that is going to transmit from from the nerves to the brain. The potential difference will be traveling. So we need to know what do you mean by the potential difference. So that's the whole chapter is about. Most of the changes occur within a millisecond. The change, when you feel the sensation into your subs, like someone pricking you, the nerve senses it. So what happens that signal is introduce a change in the nerves of the potential. There is a rest potential where inside the cell is negative, outside is positive. So when a tactile simulation happens, it just changes, and that change will be propagated across the nerve through the axon to another nerve and so on to the brain. These changes, you are all familiar with this graph, I believe, right? So it all happened in something like milliseconds, right? So the whole thing is like 8 milliseconds. So the depolarization is the first step. So the ordinary rest potential is inside the membrane is negative, outside is positive. What do you mean by depolarization? This reverses, right? Inside become positive, outside become negative by the transfer of the ion through the ion channel and so on. So this part is the depolarization. The normal polarization is depolarized. Then that dies down, so that is called the repolarization. Then you have the resting. There is what do you call? I forgot. This is there is over hyperpolarization. Then you come back to the. I don't know why it is not mentioned here. Hyperpolarization. So the signal travel from one segment to the next segment and so on. So you can see, I believe it is animated. Is it? No, it's not animated. Right. So here the depolarization occur here, then it go back to the resting potential that is carried to the next one. So that's how the signal travels along the axon and then through the synapses to another nerve cell and from there to another one and so on to the brain. So that is how the signal is transmitted. So you need to talk about the potential difference here, right? So we are laying the foundation now, so you will understand the meaning of what do we mean by potential. Right. So first, let's start with the electric energy. It's actually electric potential energy, but we drop that potential part. So you will not confuse that with the electric potential without the energy. So electric energy is actually electric potential energy. But for convenience, we drop it. But you need keep in your mind it is electric potential energy. But we just from now on, we'll just say electric energy. So for a charged parallel plate, because our nerves are parallel plates, right? The outer membrane, inner membrane, those are the plates. No. I'm sorry. So let me say this is the membrane. So this is the inside the cell, right? Inside the cell, it will be negative, right? And outside the cell, so this is one plate, which is the negatively charged. Outside the cell, this membrane will be positive. Hope I'm getting it right here. Positive. So positive, I should write here. So this is outside the cell. This is inside the cell. So this membrane is positively charged, and this membrane is inner one is negative. As the resting potential, this is negatively charged. The outside is positively charged. So we learned in the previous chapter, there will be an electric field from the positive to the negative. There will be an electric field. And the expression for the electric field is sigma over epsilon 0, right? That formula was there in chapter 17, where sigma is the surface charge density, which we assume to be the same. And that's the electric field. Now we have a small confusion with the symbol, can't help. The E is the symbol reserved for electric field, right? So we cannot change it. But for energy also we need a symbol. Energy happens to start with the letter E. So we have, unfortunately, we have to use again E for the electric energy. Don't confuse with the E for the electric field. But anyway, to avoid some, at least we put the subscript EL, stand for electric. So E with the subscript EL is for electric energy. E without anything with the vector arrow on the top, that is electric field. So I hope we will not get confused. No problem. This is life. Can't help. So the electric energy, because of this electric field, the potential energy, I can give the example of gravitational potential energy, right? So what happens is the gravitational force doing a work, but we can look at it like, instead of saying the gravitational force is making this come by doing work, we can think of it as energy. When the pen is here, it has a higher gravitational potential energy. So as it comes down, depending on the position, it will be lower potential energy. When at this position, it has a lower potential energy. When it is away from the surface of the earth, it has higher potential energy. Something similar happens to electric force as well. So there is an electrical field, and say the electric field between the membrane is E. We know it is a constant electric field. So if you take a positive charge Q, this positive charge Q will experience electric force in the direction of the electric field. So it will come down, right? Because the force is pulling it down. But instead of saying the force is doing work, the electric force is doing work, we can introduce the concept of the electric potential energy. We will say when the charge is here, it has higher potential energy. So when it is closer to the negative plate, it has a lower potential energy. So in the same way, I can introduce this function for the electric energy. Compare it with the gravitational energy. QM, gravitational field, okay, it's actually the 9.8, right? The G. It's a gravitational field due to the gravitational force is replaced by electric field. And why? Why? So because a constant, even the gravitational force is constant, right? It's a constant from surface level. It is a constant. So similarly, from this negative plate to this positive plate, we have a constant electric field. So this constant electric field will have an electrical energy associated with. The function is this. It's very easy to remember. It looks like the mgy, that is a gravitational potential energy, and this is the electric potential energy. Instead of M, you have Q. Instead of G, we have the electric field. Y is Y. Y is measured from the negative plate to the positive plate. The upward direction is from the negative to the positive. Okay, so that is very important. Y distance y is from the negatively charged plate. So y equal to 0 at the negative plate. So upward will be towards the positive plate. And you can substitute for E for a parallel plate with this expression. So hopefully, that's enough for you to convince that, electrical energy will have, electric field will provide, we can replace the force by the potential energy. When you say electric energy, you really mean electric potential energy, but we can drop that potential, just say electric energy. So this constant here, we already know that it's called the permittivity of vacuum, and sigma is the surface charge density. Right. So we can kind of think of it in the same way that you do the gravitational potential energy thing. Let's say we hold this charge between these plates. So it is positive, right? If you left it itself, it will come down to the negative plate. The force will be directed to the negative plate, the positive charge. So it will, by itself, it will go down. Suppose we hold it with my hand, not allowing it to, so we keep it in equilibrium. So my external force is up, the electric force is down. Electric force will be electric field multiplied by Q. All right, the definition of electric field, the force per unit charge. So force on that will be Q multiplied by E. So this is in equilibrium now. We slowly let it come down, lower it. Then what happened is potential energy, or the electric potential energy, will decrease, okay, as it comes down. Closer to the negative plate, it will decrease. So all the time we'll, the electric force will be doing a positive work as it comes down, and your force will be, the external force will be doing a negative work because displacement is down and your force is up. Okay, next slide, we can now do a question. We have 6 processes in the slide, in the next slide, where a probe charge, green circle, with positive or negative charge indicated, depends, some of them positive, some of the slide, because it is positive, some of them negative. So the probe charge is a green circle, is moved from an initial position to the final position, in which case the work done by the external force is positive, and thus the electric potential energy of the probe charge increased. So let me go back to this. Now here, when you go from here to here, right, what's happened to the electrical energy of this configuration of this charge in the electric field? It is decreasing, right? Because Q, E, Y. So as you go down, Y is, because Y equal to 0 at the negative plate. So Y is decreasing. That means this energy is decreasing. Like this pen, as it goes down, it is decreasing in the same way. Right. Now the question here, We have 1, 2, 3, 4, 6 different things. And each one, we have to tell me where the work is done on the system, so electrical energy is increasing. Let me start with number 1. The positive charge is moving towards the negative plate. So they're actually decreasing, right? Energy is decreasing. So why? The direction of the electric force is this way, Q is positive, right? And E is always from the positive to negative. Yeah, I'm explaining that, okay? I'm explaining, I'm going to explain. That is what I'm doing now. You are asked the question, right? So I'm giving the answer now. Listen. Why is it positive, right? That's your question. Why, which one? Electric field is positive? Yeah, okay. So you going to, I didn't say positive, I didn't say it is positive. Positive what? The question is, let me repeat the question. What is the question? The question is in which one of them we have the external force is doing a positive work, where the external force is doing a positive work. So the energy is increasing. Energy of this system is increasing. The system goes from the positive charge here to the positive charge there, right? So what happens here is the work done by the field itself is positive. That means you are doing a negative work. So the system is not increasing its energy, it's actually decreasing the energy. Let me prove why this energy is decreasing. Let me put it that way. I want to show here, for this case, the energy is actually decreasing. Shall I do that? No, the system is doing the work. Remember our thermodynamics? If the system is doing the work, it loses energy, right? If we do the work, it is getting the energy. So I'm going to show you here, the system is doing the work. Because the force on the charge will be to the right, right? Q is positive. Electric field is also to the right. So the force will be to the right. The force on the charge will be to the right. And it is moving to the right. So the work done will be by the system will be positive. So the system is doing the work, its energy is decreasing. You are not providing an energy, it is doing by itself, like the expansion in the system is doing the work. That means the energy has decreased. So he is out. What is the question again? The question is find the configuration where you provide energy. So the work is done on the system to bring it from the lower energy to higher energy. Here it is going from higher energy to lower energy. So this is the system is doing the work. So it losing its energy. So he is out. What about number 2? Yes. Because now you are forcing it, because this is the initial is this, right? Here. Sorry, this is the initial. Because how do you know which is the initial? Arrow. From the arrow. So you are going from a negative charge is forced to move to the negative plate. Can it do it by itself? No. You need to provide the energy, right? So you can look at it the way I did for this. What is the direction of the force? Electric field is like this. This is the always electric field from the positive to negative. So this is the negative charge. The force on the negative charge will be in the opposite direction to the electric field because Q is negative. So the charge will feel a force to the right and you are forcing it to move to the left. So what is happening here? You have to provide, you are bringing it from the lower energy to higher energy. So externally you have to apply the force. The external force will be in this direction, and the displacement is also to the left. If both are in the same direction, it's a positive work. So the work done by the external force is positive. So it will give that energy to increase its previous lower energy to now higher energy. So number two, now you get the point, right? So number two is yes, here we have to do a work, positive work. What about number three? No change here. Why? Same energy, right? The energy depends only on the y. It is the same y. QE y. Y is the same, no change. It's in the middle, is the same potential energy. What about this? Yeah, you are going against, so that, yes, this is also one of the choice. This. You have to provide energy because you are increasing it. What about this guy? No, it is going by itself. So you still do the work. So it is going from higher energy to lower energy. That's what it will do anyway. This one, no change. Okay, so he's out. Only these two are where you have to provide the energy. So it is brought from a lower energy to higher energy. So you give energy function when we have a constant electric field. This is the equation. When the electric field is constant, where E is the constant electric field, the electric energy is given by this expression. Yeah. I didn't quite understand. Uh-huh. No, it's only one charge. No, we are talking about one charge. This is one guy. This guy is brought from here to here. It is not two charges. No. It is. We are talking about one charge moved from here to here. When it does that, what is happening to the energy of that system of the field plus the charge? It is not two charges. Okay. Yeah. We have two plates. And there is an electric field. Yeah, that's it. Okay. Okay, right. Now, that is the electrical energy for constant electric field. We have a constant uniform electric field, and we put a charge and see what is happening to what is the electric energy for a constant electric field charge system. Now we come to another for a point charge, not for a plates, not for a uniform charged. Only in a capacitor plate we have the uniform electric field. For a charge, point charge, do we have a uniform electric field from a point charge? No, it's not uniform. If you have a point charge, the electric field is, this is the electric field. It is a function of R. As R increases, electric field will decrease. A function of R is not uniform. When you have a point charge, we will have an electric field which is not uniform. It changes with the distance to the point charge. In such an electric field, the electric energy is given by this formula. Yeah. I'll come to that, but let's get the concept. Okay. So before I gave the electric energy for a uniform electric field and a charge, interaction between a uniform electric field and a charge. Now I am going to get the electric energy in a non-uniform electric field. When you have a point charge, the electric field is non-uniform. It is not constant. It changes with the distance. And if you remember, now again, you should not confuse. I'm writing for the electric field, not energy, which is K Q over R squared. It's a function of R. Now, when you have such an electric field due to a point charge, the electric energy, when you bring a probe charge, Q, So suppose this is the electric field created by this um, capital Q. Okay, so there is an electric field like that. If you bring another charge into this electric field, say small q, the energy due to this field plus charge system is given by this equation. Okay, Q into E. E is this and multiply by Q. So that will give you the electric energy between a non-uniform electric field created by a stationary point charge of capital Q, and you place a small q in that electric field, the energy due to the interaction between that electric field and the charge is this equation. So just remember this equation, okay? So I gave an equation before that is for a uniform electric field interacting with the charge Q, small q. Now we have a non-uniform electric field, which is actually function of R, and you bring a probe charge, okay, Q, then because of the interaction between this probe charge and the electric field from the point charge, the electrical energy is given by this equation. Yeah.
Take K about 1/4 you can choose the difference. Okay?
Yeah. The electric field, okay, now this is electrical energy. K is actually this. This is K, right? Then we need to find the energy. It means the finding from going from here to here is complex. I mean, we need integration and all. The work done is and so on. So I'm skipping a lot of things in between. So I mean, this is electrical energy, this is the electric field, and you have a charge Q. The electric field has the big Q, okay, forgot the big Q. Then we need to do integration and so on because it's not a constant electric field to arrive at this equation. You don't need to worry about that, okay? This is more than enough. You just have the equation. Just have the final result. Because of the interaction between the electric field due to this point charge, which is non-uniform. For a uniform field, it is easy to prove that equation. Even there, I didn't bother. Here, I shouldn't bother at all because it involves integration and so on. So what you need is this final expression. This equation for point charge. Okay, when you have a point charge, it will create certain electric field. It's non-uniform, and the interaction of that electric field with a probe charge Q, when you bring it to that, the energy of that system, the uniform, non-uniform electric field with the point charge, how they interact, there will be an electrical energy. This is the expression. All you need to know, there is a certain expression for a potential energy for a stationary point charge, its interaction with the probe charge small q. So with this equation, you can see that when R goes to infinity, what happens to the electrical energy? 1/infinity is 0. So say let's say about this Q, big Q, say positive. At infinity, if you keep a charge at infinity, no matter what its value is, the potential energy of that system is 0. But as you bring R smaller, as you bring closer and closer to this, the energy will increase, right? Why? When R becomes small, 1/R will be bigger and positive. Because you have to put the put this with the sign, right? You said this is already positive, and let's say this is also positive. Positive multiplied by positive will be positive. So that will be a positive quantity. So when you bring another positive charge from infinity to closer and closer, increase, energy will increase. Actually, you know, you need to give some work because you are fighting against the repulsion, right? Positive will repel each other. So you want to bring it closer, mean you have to supply the energy to bring it closer. So you are going from lower energy to higher energy as you bring it closer and closer. So everything makes sense, right? Let me say If it is negative charge, the big Q is also negative, and the small q is also negative. Same story, right? Yeah. Same story, yeah. Because negative will be positive. At infinity 0, as you come closer, it becomes bigger and bigger positive number. Now let me say this is positive, but the small q is negative. When it is at infinity, 0 anyway, because 1 over infinity is 0. But as you come closer, what happened? Increases, but the negative number. Increasing, but negative number. Which is bigger? Big negative number is big or small negative number is big? Small. So as it, yeah. I'm asking about the energy. Energy is given by that expression, right? The energy between a point charge and another charge at away from it. Say this is positive, the other one is negative. Positive multiplied by negative is negative. So let me put some numbers, okay? Let's say R is equal to, say I will keep 100 meters away, and I get this energy to be negative. Anyway, well, let me 100 meters away. Let me say I got a number minus 155, let's say, joule. It's negative, right? Small q is positive, big q is positive, small q is negative, positive, negative will be negative. So minus 100. Now I make this R to 50 meters. What happens to the quantity? Increase. But then E2 will be, that is with the 50 meters, it will be increased. But it's a negative increase, right? Minus, let's say, 285 or something. Just putting some numbers. Which is greater? E2 is greater or E1 is greater? E1 is greater. So as you bring it closer, what is happening to the energy? Wait a minute. You make it 50, right? When it 50, this number is greater. I mean, numerically greater. But which is a big number? Minus 155 is big number or minus 285 is a big number? E1 is, so when it is far, it has more energy. When it is closer, it has less energy. So energy has decreased. Right? I hope it is clear. Right? You forget about the number, that's what you expect, right? Because it will come by itself. The one capital Q is positive and the small q is negative. So it will be attracted. So it will automatically, the energy has to decrease. So it makes sense with the numbers as well. So don't look at just the number, you look at the sign also. So you know, although E2 looks bigger, it's actually smaller. Yeah. What about you? Same story. Same story. Yeah. You don't have to discuss that. Because one is positive, one is negative, it's attraction. So it will come by itself. The energy is decreasing spontaneously. It will come to a lower energy. Yeah. No. Okay. So, yeah. Because the product, you have to look at the product. The product is negative. Right. So we got that out of the way. Electric energy, we had two formulas, right? One is for constant uniform electric field, which is QEY, and one for non-uniform electric field, which is the previous expression. So, it will be the formula sheet, okay, even if you forget, no problem. Now we go to the other concept, electric potential. Right. Remember the force and field. Force is something, field is another thing, but they are related. After you define the electric force, we define the electric field. We say the electric field is an abstract concept. You don't need two charges. We can define the electric field for which field coming from just one charge. We can imagine there is a virtual force there. So it's a field. Electric field is a force. If I bring a probe charge of a probe positive charge of unit charge bring to that place, the force experienced by that probe charge is the electric field. In other words, force per unit charge. So it's an abstract concept. In the same way, we can define the electric potential also from electric energy. So we already know the electric energy. So what is electric potential? That we define a field called the electric potential. The symbol is V. Okay, it is not electric energy, it is electric potential. Not electric potential energy, it just stop electric potential. The symbol is V. That represents at every position in space the electric potential energy that a positive probe charge of unit charge, in the same way that we did for the electric field, would have if brought to that particular point. It is in terms of the energy, right? The energy that a positive probe charge of unit charge would have if brought to that point. So you define a potential at that point. Then once you have it, you can throw away the probe charge. We don't need it. Per unit positive charge, the potential energy that will be there is called the electric potential. It's a field. It's a scalar field, not like the electric field. Scalar means it has no direction. It's energy. Energy is not a vector, right? Energy is a scalar. So it's a scalar field. It is labeled V. The label is V. Probably you heard the word voltage, right? It is the same thing. Okay, but voltage is used in circuits, electronic circuits. But here it's not about, in general, it's the potential. And it is defined as the electric potential energy, which is the E, per unit charge of the probe charge Q. As a consequence, is the interaction with the remaining stationary charge in the system. If you have in the system, there will be some electric field created, right? So because of that, there will be electrical energy when you bring in another charge. If that bringing in charge has a unit positive value, then we say it is the electric energy at that point. So in other words, I can say the potential is electric energy per unit charge. Like the electric field is electric force per unit charge, in the same way, look at the similarity. So the potential is electric energy per unit charge. Right, now we got the two expression, right, for the energy. We have the energy for parallel plate, which is QEY. Then we have the energy for point charge, which is K Q divided by R. K is 1/4πε0, so it is easy for me to put it this way. So with these two expressions, one is for uniform field, the other one is for the point charge, right? So now I can get the potential for this case and the potential for that case. So all you have to do is to take the energy and divide by Q. So when you divide by Q, this Q goes, we get this expression. And for the point charge, when you divide by Q, that Q goes, you get this expression. Simple as that. Okay. Okay. So all these expression will be in the formula sheet. All you have to know that we have defined this electric energy and the potential for two cases, right? One is for just the constant uniform electric field, the capacitor plate, and then stationary point charge, that's the second one. Okay, what's the time? 1:45. Let me see how much we can cover. Yeah, okay, maybe up to this question. Oh, we have printed. I need to pause. Consider the potential curve V shown in the next slide. Which of the four charge parallel plate arrangement is consistent with the potential curve shown below it? So this is the curve. But this curve only represents one of these four. Okay. We need to find which one this corresponds to. Let's start with the A and draw the curve ourselves. Curve of what? Potential against X. The X is this, right? X is here, the X is along this. He is telling us, take the X along that line. So when X is equal to 0, as the X changes, will the potential change? What is the expression for parallel plate? V. We had it E, Y, right? The Q can cancel. For parallel plate, the V is equal to just EY. Y is the distance that we are measuring. Okay, so Y measured from the negative plate to the positive plate, right? So here, what is this X? X is this. So when you change the X, is the Y changing? No, it's the same Y. So potential versus the X, you should have the same potential. I know it is a bit confusing because I have Y and X and so on. Now, potential for a parallel plate is given by this expression. So in a capacitor plate, the potential at the negative will be 0. At the positive plate, it will be some maximum, let me say 100 or something, okay, volt. By the way, unit, we did talk about the units? I think I missed it. Voltage, yeah. How come it is may not mentioned? This is energy, right? This is energy, and this is coulomb. But this has a name, volt. I don't know why it should have mentioned that. Okay, joule per coulomb, but it has a name. We don't keep saying joule per coulomb. We say volt. Potential is actually voltage, volt. So now let me go back. Right. So if you take somewhere here, what is the Y value everywhere? Same. That means the potential everywhere will be the same. So when a graph that is for this is your X. So whatever the X value, the potential will be the same. So this doesn't correspond to this. This is a changing. So he is out. This graph is not for this. B, the same thing. It could be C or D. Which one it is? Let's take the C, for example, okay? And Y is measured from here. Y equal to 0 is here. From the negative to the... So, X is going to the right, right? So, when the X increases, what happens to the potential? Potential should... Wait. Potential should... At the positive, it will be high, right? So when you go to the right, the potential should decrease. Potential decrease. So here, you are going from here to here. It will be, it's outside, right? So it will be the same value. When you're going here to here, it should decrease. But here, it is increasing. So this is also out. So it is D. So you are going from negative to positive, it is increasing, and then again it comes constant behind. So it is D is the answer. Yeah, only this, then we will stop. Yeah. Yeah, sure.
Yeah. The direction of Q, is it positive or negative?
Direction of E. No, Q.
Yeah.
Q is a
I
charge.
mean, is it positive or negative on C?
C. All right. Let me do that again. So let's look at C. So let's look at C, right? The potential function is V is equal to EY. Okay. Y is equal to 0 here, and the direction of Y is this way. Y goes this way. The potential at any point you will get from this equation where Y is measured from the negative place to positive place. That you have to remember that. Now you got it. So when you go this way, so if the potential is 0 here, then it will become 5, it become 10 and 15, maybe 50 or whatever. So this way the potential is increasing. So when you go along the x-axis, from here to here, the potential will decrease. So that means this is not the correct one for this. Yeah. Potential will be given by E into Y, right? Potential is given by, in a parallel plate, constant uniform field is given by EY. Y is measured from negative plate to positive plate. Got it now?
Yeah.
Okay. Is it fine now? Right. So let's do this one. If the electric field has a constant magnitude and points in the positive x direction, which of the following formula is correct to describe the potential if A is constant and B and C are positive, non-zero constant? Okay. So the V has a constant, like the parallel plate, constant magnitude. The electric field has a constant magnitude. Its point in the positive x direction. So the electric field is point in the positive x direction. Let's say this is the x direction. So the electric field is also in the positive x direction. Let's imagine. So the potential will be maximum to the left or to the right. It will maximum to the left. See, you can imagine electric field go from positive terminal to the negative plate, right? Positive to negative plate. So which is at higher potential, positive plate or the negative plate? Positive plate. So the potential is higher. I put it this way. The potential decreases in the direction of the electric field. Maybe that is easier. So how do you remember this? Potential decreases in the direction of the electric field. That's much better. So no confusion. Remember that. Potential decreases for a constant uniform electric field in the direction of the electric field. So that means if the direction is to the right, as you go to the right, electric field will decrease, right? Potential decreases in the direction of the electric field. That's what you have to remember. Now you can answer this question. If you want to write any formula with V as a function of x, V as a function of x, when x increases, my potential should decrease. See, he is telling us electric field in the direction of x, right? Then I am telling you, this is general truth, okay? This is given to you. Electric fields in the, for this question, electric field is in the direction of x. Now something you have to remember, the general truth is potential decreases in the direction of the electric field. Okay, that's a general truth. Right. What you have to remember is potential decreases in the direction of the electric field. Okay, that's clear. Potential decreases in the direction of the electric field. Now, this particular question, he says the electric field is in the x-axis, in the positive x direction. So you are asked to write the potential as a function of x. So the function should be such that when x increases, potential should decrease. Okay. Now let's take this. Is this correct?
No, it's got
It's not a function of x at all. It is a constant. So he is out. What about this? A and B are constant. When x increases, potential increases. So he is also out. What? Yeah. Okay. X increases, this increases versus negative number, right? So, all right, done. Now, when we can have complex ones, so we may be asked to find electric potential for more complex arrangement, not just one charge, maybe several charges and the combination of them. In those cases, we have another way of doing it by using equipotential lines. You know what is equi mean? Equi mean equal. So if we can find, rather it's a surface, though we call it lines, in a line, let's say imagine a line in a 2-dimension, and everywhere on the line we have the same potential. We call it equipotential line. Okay, so that's the meaning of equipotential. So equipotential lines are lines that connect points of equal values of electric potential. So that's the definition of equipotential line. These lines, without proving and etc., we'll just say are always perpendicular to the electric field line. Okay, it can be proved, but no need to bother. So we know how to get the electric field line, in a certain small system, like just one point charge system, the electric field line. So for example, we can take first one, the easy one. So the capacitor plate, between the capacitor plate, the red lines are the electric field line. The dashed red lines are the electric field line. So you know the equipotential line because a function of the y position perpendicular to the plates. So any line that is perpendicular to the electric field line is a equipotential line. So all these green lines are lines with the same potential everywhere on that line. So this, which is closer to the zero, maybe this one will be the zero equipotential, the one that is exactly on the negative plate. So everywhere on this, the potential is zero. So as you go away from the negative plate, each equipotential line will have a greater and greater value. So maybe this here is all, say, 1 volt. This is all 2 volt. This is 3 volt potential line, 4 volts potential line, and so on. So that's the green lines are all separately equipotential lines. Okay, right. So this is for the uniform electric field like that in a capacitor plate. B, this is the for a point charge. So the electric field lines are those red arrows, okay, radiately outward from the positive point charge. So any circle concentric with the charge is a equipotential line because you know the potential is the function of 1 over r, right? So if r is a constant, v is constant. So any circle concentric around the charge with the center at the charge is a equipotential line. Actually, it's a sphere, right? Because if we are thinking in 2-dimension, it is a line, but any sphere with the same radius, with the center at the charge, is a equipotential surface. So rather than saying line, we can say all the sphere around the charge is an equipotential surface. So now for a complex arrangement, not just one charge, 2 charges. This is a dipole, right? We learned that if you have 2 charges of same magnitude but opposite sign, we call it electric dipole. So for the electric dipole, first you know what the electric field line is. The red dashed arrows are the electric field line. So we can simply know in the fact the potential line or the surface must be perpendicular to the electric field line. So it closer to the charge, it's almost a circle. But away from the charge, it become more elongated circle. Okay, so as you come closer to any of the charges, it will be a circle centered around that charge. But as you go away, in the middle, the equipotential line is just a line. It's rather, if you think three-dimensional, it will be a plane, a surface. Okay, so that is equipotential surfaces or equipotential line. Now we come to apply the conservation of energy principle when we have potential energy from electrical energy. So what is our conservation principle? Suppose if you have an isolated system, the net change in the energy is zero for an isolated system. For an isolated system, when there is no, any non-conservative forces like friction and so on, then we can say the mechanical energy does not change. That means there may be a transformation from one form to another. So the kinetic energy can decrease, say by 100 joule. What happens? The potential energy will increase by the same amount. So the total change is zero. So here we are looking at an isolated system with no any other non-conservative forces, only considering electrical energy, electrical potential energy and kinetic energy. So because we are now looking at particles, right? Particles, the masses are very small. So we can ignore completely the gravitational potential energy, the energy coming from the gravitational force. If the masses are small, gravitational force is small, we will ignore that. So in such a system where we only have small particles, where we can ignore the gravitational potential energy changes, so it will be simply kinetic energy change plus the electric energy change must be equal to zero if it's an isolated system and no non-conservative forces acting on it, friction losses, etc. This is the equation we can apply. So this equation can be given like this also. Okay, change, or you can say initial energy is equal to final energy. That means the total change is zero. So we can now answer a question by using the law of conservation of energy. This is the famous experiment done by this scientist called Rutherford. You all know he's the one who gave the structure of the atom. People discovered the proton and electron. They know positive charges proton, negative charges electron, but they didn't really know what is how the atom is consisting of. They first thought maybe protons and electrons are all jumbled up like a pudding distributed evenly. But when they did this experiment in 1911, if that is the case, they took a gold foil and they shoot alpha particle, alpha ions, which is positive, two positive, right? So they have protons, two protons, in electrons are stripped. It's supposed to pass through because a thin gold foil, but sometimes they observe there's a sharp U-turn. Sometimes this proton take a sharp U-turn, 180 degrees turn. It's only possible if the protons are concentrated in one location in the nucleus. Okay, so that's how they explained it and how they gave the structure of the atom. So most of the time it just passed through. Okay, so like empty space, nothing happens to the proton, it's not deflected. But time to time, they take a U-turn. So the experiment was explained with the model of atom with the protons are in the nucleus in a very small volume with the neutron and the proton, and the electrons are like a fuzzy cloud orbiting around this almost an empty space. Right. So what we are going to do now here is to apply the conservation of energy principle to get the radius of uh, the gold atom. How? This is how. So we saw this alpha particle, which is two protons here. It is a charge is 2e positive. So it was shot at this with a speed of v0, let's say, and it comes as close as possible, but this is a gold, it's a nuclear, it is still stationary, and it is highly positively charged. I mean, we forget about the electron, this nucleus is, so when it reaches that, it will feel the repulsion. That's why it is taking a U-turn, a complete U-turn. So the closest approach, when it is closest approach, what is the velocity? Zero. That's why it's changing the direction. As it comes closer and closer, what is happening to its kinetic energy? Decreases and come to a zero. So where did this kinetic energy go? It becomes the potential energy, electric potential energy due to the electric force between these two guys. So as it comes closer and closer, the potential energy increases, right? But it has got some kinetic energy. Where is the energy coming from? By the loss of this kinetic energy. So here it has kinetic energy is very high, okay? It will be half m v0 squared. And we can say compared to this distance, this is far, very far from there. The distance is like infinite distance. So the potential energy is zero. Electric potential energy is zero when they are far apart, okay? So 1 over r, if r is infinity, theoretically it is zero, but it's not infinity, but still it's a very big distance compared to the when it is very close. So we can say it is zero. Here, potential energy is not zero. As it comes closer, it is K, Q1, Q2 divided by R, the distance between them, the minimum distance, whatever. But the kinetic energy is zero. Potential energy final is this much. So all you have to do is to apply the conservation of energy. We'll say initial energy is equal to the final energy. Okay, so that's what you are going to do in the next slide. Oops, I went the other direction. Oh, no, right. If an alpha particle, just describe in the question again, on a path leading to a head-on collision with a gold nucleus has a speed of, so we are giving the V0 value. While it is far from the gold nucleus, how close it gets to the gold nucleus? So we have to find the D minimum. So at the D minimum, as we discussed before, the speed is zero. So we need this value also to answer this question. So we say this total energy initially equal to the total energy finally. Total energy initially is the kinetic energy of the alpha particle, which is not zero, it has certain velocity. But when they are far apart, I can consider this to be zero, the potential energy. When they are close, the closest distance, the kinetic energy, because taking a turn, it's about zero. And this is by definition the potential of a potential energy between two charge particle is this. Okay. So Q1, Q2, Q of the alpha particle, Q of the gold particle, divide by the, yeah, here everything is given. Well, it's a homework, example problem, so we can get the values from the table. We only assume we don't know what the D minimum. The question is to find the D minimum. Well, Q is given in the sense alpha particle mean 2 proton. So one proton has a charge of 1.6 10 to the minus 19. 2 proton will be 2 times, okay, 2e. For the gold particle, if you know the Z number of the gold particle, which from the periodic table, so I think we saw that gold particle before. Count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So maybe Z number for gold particle is 13. That means it has 13 protons. Yeah, 13 multiplied by E. Anyway, I think, yeah, no, 79. That was just a schematic diagram. So it is not 13. 12 is carbon is 13. Gold is very heavy. Yeah, it is 79 protons. So Z number is 79. Yeah.
We use the charge of electrons, right?
Yeah, yeah. E, because proton and electron has the same charge. Only one electron is negative, proton, we just need the magnitude of the charge. Yeah.
Sometimes they differ because of isotopes.
Oh, yeah?
Yeah.
Yeah. No, no, wait. Z number doesn't change. Isotope, what changes is the number of neutron. Okay? It be. Am I right? Yeah. Okay. Yeah, only the mass only. Z number defines the. What do you mean by isotope? Yeah. That, same. So I'm right. Okay. All right. Okay. Right. Anyway, now you just substitute and find it. Yeah. Because when the proton number changes, it becomes another element. It is not the same element. Yeah. So that's what I said is correct. Isotope means it is the same element. That means proton number doesn't change. What changes is the neutron, number of neutron it's going to have. Right. Capacitors. So, capacitors mean, two plates, there's a charge separation, equal magnitude, but, one plate is positively charged, the other plate is negatively charged. Like in the nerve membrane, that's the case, right? We have. So, the potential difference, if I say delta V between the positive plate and the negative plate, right, the potential difference, because one is positively charged, one negative, there'll be a potential difference because of the separation of the charges. That potential difference delta V across a parallel plate capacitor is proportion the charge on the plate. If you have any, one of the plates, okay, because the same, if Q here also Q, this is positive Q, this is negative Q. It is the same magnitude. So it's proportion this Q on the plate, the charge on the plate. If you have more charges mean, the potential difference will be greater. So the proportionality constant is called the capacitance of this capacitor. We have a name for two parallel plates with the charge separation. They are called capacitors. So the charge on one of the plate is Q, and it is proportional to the delta V. And we say the charge divided by the potential difference, we call it capacitance of that capacitor plate. Capacitance. Yeah. And the label we use is C. No, it depends on the, because if you, for a given plate, it has a given value for a given plate, okay? So what happens when you increase the charges, the potential difference will increase linearly. So that means capacitance for that given plate is constant. We can construct another capacitor plate. It will have a different C. It is a given property of a given capacitor. Okay, so for example, your nerve cells will have a certain capacitance, but you can have some capacitor, physical capacitors with different values of capacitance. Okay. Right. It is like how much charge it can hold. So the word capacitance, you know what the meaning of capacity is. So how much capacity that plate has to hold how many coulombs in it. So in that sense, the word capacitance, okay, the capacitance. So if some capacitor plate has high capacitance, that means it can hold more charge for the given value of potential difference. Okay. If you have another capacitance, the poor capacitance, then for the same given applied voltage, it will carry only smaller amount of charge. So you have to understand in that sense. Right. So here we are looking at these parallel plate capacitors. So between the capacitors, this is vacuum or insulation. Okay. So the charges will be separated because they cannot go through this. This is electrically insulated. Vacuum means nothing can pass through there, right? Nothing. So even if you put like a rubber between, rubber is not a conductor. So can the charge pass through it? No. So there has to be a gap. Air is also a good insulator. It can be something like a rubber or plastic or something which does not conduct electricity. So for the capacitors, we have some geometrical things. The area of the capacitor plate, the overlapping area of the capacitor plate, it will have a certain area. And the gap, the gap between the two plates, we call it B here. So these are the property of any capacitor for a parallel plate capacitor. In terms of these two, we can that can determine the capacitance of a capacitor in addition to another factor. So here we are showing that again. So the plates, two plate must be a conductor. The two plates must be a conductor, and the gap must be insulated, should not conduct electricity. So when you connect it to a battery or apply some potential difference, you will have one side will be positively charged, the other side will be negatively charged. The capacitance of a parallel plate capacitor depends only on the geometrical property. So it is going to be proportional to the area, because bigger area means it can hold more charges, right? It's understood. It is directly proportional to the area, but inversely proportional to the gap. If they are close, it can hold more charge because the charges can influence each other, keep them. So if they are big separation, the capacitance will be less, smaller. So it is understood intuitively. And there is got another constant that comes in, which comes in our Coulomb's law as well, 1 over 4 pi epsilon 0. Okay. So this is the permittivity of free space. Now we can make sense of this epsilon 0 by thinking in this way. Imagine we have a capacitor of unit area, that means A is equal to 1. And imagine the gap is 1 meter unit distance. Then our equation Q is equal to CV, and C is epsilon 0 A over B. So that's what he said. It depends. If we make this 1 and this also 1, you can see that the epsilon 0 is the proportionality factor of the charge brought onto the plates and the resulting potential difference between them. So this epsilon 0 is now replacing the C. It's plays the role of the proportionality constant between the potential difference and the charge on the plate. Thus, this epsilon 0 is a measure of the ability of the electric field created by the charges on one of the plates to reach through a vacuum and affect the charge on the other plate. So to maintain that potential difference, if the epsilon 0 is a measure of how much it can maintain that potential difference. Okay, right. Right. Now, so we said the gap can be vacuum, nothing, or air. Air is a good insulator, but it can also be some other material, as long as that material cannot transfer the charges between the plate. If it's an insulating material, good. We can use between the plates, we can put any insulating material. Michael Faraday, okay, this is a experimental physicist, determined in 1837 that all electrically insulating materials qualify for what we can put in between the gap, any insulator. But it has a special name. We don't call it insulator. When you put it between the capacitor plate, it gets a new name, dielectric. Okay, so it must be insulator. But when it is used as a material that kept between the capacitor plate, we get a new name for him. It is called dielectric. Right. So when you put the dielectric, what happens to the thing? Previously, with the vacuum, C is equal to this. This is what we give. Now, the moment you put the dielectric, it increases by a factor of kappa. This looks like K, right? But actually, it's a Greek letter. It is pronounced kappa. Okay, it looks like K. It is the same sound probably in Greek, but its name is like alpha, beta, gamma. Its name is kappa. So sometimes people just use K, but K have a problem. You know why? K is also the constant that comes in the Coulomb's law. So it is not the same. So that's why probably we use this kappa. It looks a little bit like a capital K written like a small k or whatever. Anyway, it's kappa. So when you put a dielectric, any dielectric has a characteristic value for that kappa. So mica is an insulating material, has a certain value of, it is called dielectric constant. This kappa is called the dielectric constant. So rubber will have a certain value for kappa, and mica will have another value. The in your nerve cells, the bilipid, whatever that thing will be our insulator. That will have another value for its dielectric, phospholipid dielectric constant. So we can see a table coming up. Yes, good. Nerve membrane. The insulating material between the two membranes, which is literally the phospholipid bilayer or something, its dielectric constant is very high, 7. So actually it increases the capacitance of the nerve membrane. If it is just vacuum, it is just 1, right? Because of this nerve membrane, whatever the fat lipid layer we have between the membrane, it has a value of 7. Air is almost like vacuum. Polystyrene, paper, Pyrex glass, porcelain, they're all insulating material. Silicon is high, ethanol, water is even higher. Okay. Come on. This is the last slide for this chapter. Energy stored in a capacitor. So capacitor has an electric field, right? So that means there's a separation of it. It's like a battery, like one side positive. So it has energy in it in the form of electrical energy. The energy stored in the capacitor is given by this formula. The electric potential energy half. Okay, half is half. Q is the charge on one of the plates. Okay, the magnitude. Delta V is the potential difference between the plate. So this is the formula for the electrical energy stored in that capacitor. But then by using the formula for capacitance, we can say, suppose maybe delta V is not given in the question. Then you can substitute here delta V is equal to Q over C and put it in there. You get this equation. So even without knowing the delta V, I can get the electrical energy in the capacitor plate. Maybe Q is not given. In that case, I will say, oh, Q is equal to C delta V. I put it in here. You get this equation. So depending on the question, you can use one of these 3 equations to find the energy stored in a capacitor.